also be able to tell me the name. Okay, but like I'm not going to give you like PT, which is platinum, but I'm not going to give you that and then expect you to actually know the name. But for the first 1 through 20, and then those 10 extra ones, those you should be able to name and spell. But what you also want to notice is when you look at the periodic table, do you notice that the atomic mass, the mass number that's at the bottom, has all of the decimal places on it? When you look here, so when you look here, so you see like calcium, it's 40.08. But we said initially Ca, and this one's 20. So we know that that's got 20 protons and 20 electrons because the atomic number, the number at the top. And that really defines what that element is. But the 40.08, I told you to round to the nearest whole number, subtract the 2, that tells you numbers of neutrons. The whole reason that it has this decimal place, how they're not all just whole numbers, is because there are some atoms with the same number of protons, same number of electrons, but they can have different numbers of neutrons. And if they have different numbers of neutrons, that makes them isotopes. Same number of protons, so atoms with the same number of protons and electrons, same atomic number, same name, but they differ by numbers of neutrons, and that changes their mass. Because remember, protons and neutrons each give the atom an average mass or a relative mass of 1. So they differ in numbers of neutrons. So therefore, they differ in atomic mass. These are isotopes. So you can indicate the exact number of neutrons that an atom has if you're talking about an isotope by writing it. The element, the atomic mass goes above, the atomic number goes below, sort of slightly to the left of the element. This would be carbon with atomic mass of 12, atomic number of 6, 6 protons, 6 electrons, but then it would have 6 neutrons. Just by subtraction, you'd figure out numbers of neutrons. But you can also have this. So C13 is going to be carbon because it's got 6 protons and 6 electrons. But it's going to have 7 neutrons. It has 1 more than like the typical does. In fact, with carbon, there's even a third type of carbon that has an atomic mass of 14. 2 extra neutrons than what you typically see. All it does is just change the mass. It makes the nucleus of the atom a little bit bigger by adding those extra neutrons. So if you see an element written this way, it's actually defining a specific isotope of the element. So it's telling you exactly how many neutrons. So if I just ask you based on the periodic table, you just take the atomic mass and round to the nearest whole number, because that's actually going to tell you the most common isotope. So this one, they would call carbon 12. This one is carbon 13. This one would be carbon 14. So if you see the name of the element with a number after it, that's telling you the atomic mass. It's just telling you the numbers of protons and neutrons for that specific isotope of that element. So this is why, like calcium 40 and calcium 42, they're both calcium, which means they both have an atomic number of 20. So they both have 20 protons and 20 electrons. Calcium 40 has 20 neutrons. Calcium 42 has 22 neutrons. So in writing them this way, you can specify the mass of a specific isotope versus just saying calcium in general. But again, when we look at calcium on the periodic table, we said it's 40.08. Yeah. So if you look at the periodic table, one, do note that the numbers are switched. When you're writing it in terms of a specific isotope, do you see that the atomic mass is on top? The atomic number is below. That always throws people because when you look at the periodic table, what number's on top? The atomic number. So they're like switched. On the periodic table, atomic number's on top and the atomic mass is on the bottom with the decimal. But when you write it as a specific isotope, they always put the mass on top and the number below. This seems a little backwards. I'll just point it out so that it doesn't kind of seem like, you don't go back and go, well, why is that number bigger? Okay, because it's actually, they do flip those two terms. But if you look at the atomic mass, it's 40.08 according to the periodic table. So which of these two isotopes do you think is the most common? Calcium 40 or 42? 40, because it's closest to the average atomic mass. So they actually figure out the average atomic mass based on the relative abundance of these different isotopes, because they're not all found at the same amount. So if you look at carbon, almost all carbon atoms, so if you counted 100 carbon atoms, 99 of them would be carbon-12. So 99 of them would be a carbon with 6 protons, 6 electrons, 6 neutrons. About 1% of the time, you would see one that had 7 neutrons. That would be carbon-13. So see how it's much lower? And extremely rare, so you'd have to count like 1 trillion carbon atoms, and you would see 1 carbon-14 atom. So that one's extremely small. They're not all found in the exact same amount in the environment. There are some that are found just a few, some that are much more abundant. And this is why the atomic mass, it's really an average. It's an average based on the abundance of the different isotopes in the environment. So when I tell you to determine the numbers of protons, neutrons, and electrons based on just a symbol in the periodic table, I'm really asking you to tell me the most common isotope. The most common isotope for carbon is carbon-12. And so just rounding the atomic mass on the periodic table is going to get you to the closest or most common isotope form. So what is special about these isotopes? Not all, but some of these isotopes, especially isotopes that have more than normal numbers, of neutrons, they tend to be less stable. So as they try to achieve stability, because that really is like the goal of everything, is to try and create a more stable interaction. So atoms may release energy. As they try to become more stable, that energy is nuclear radiation. So it means nuclear because it's coming from the nucleus of an atom. So that's where that terminology comes from. Elements that emit this radiation, they refer to them as being radioactive. So this is a really pretty young or new branch of chemistry. It was really only described right around 1900. So it's only about 125 years old. So all the other atoms, like they knew about some of these like centuries ago. But here, this is really pretty new. And so it was a French scientist that was collecting samples of Earth and separating it into its elemental forms. So one of the samples that he extracted and isolated contained uranium. So they were in the process of trying to describe the characteristics of uranium. It's a pretty rare element to be found on Earth. He found that he had photography film. And so back then, photography film was like really big plates of film. So he got it in the lab, took images with it, went and developed it, and it was completely white, as if somebody had taken it outside and like left it in the sun. So he like ordered some more, put it in the lab, used it. When he went and developed it, was completely white. So he was like, I know that I didn't mess this one up because I went and ordered more. And so he went through and started putting it in different places for different periods of time in the lab. And that actually led him to this one sample. Whenever the photography film was close to that sample, it would show that it had been exposed to light, to energy. And so he hypothesized this is where this energy is coming from. It's not glowing. I can't see any light, but there has to be energy coming from this sample that is causing this exposure. So he was really one of the first ones to describe this radioactive energy, this energy that can spontaneously be released. The bigger an element is, the more neutrons it has, the greater the issue is with stability inside of the nucleus. Because remember we said in the atom, you got that little space, and in that little space is where your protons and neutrons are. And those are the ones that have mass. So if you start having more and more neutrons in that nucleus, they shift. They're constantly like trying to sort of fit in a more condensed space than there is room, and they release that energy as they do that. Some molecules or some atoms in this breakdown, they actually break down into other atoms. So they called that radioactive decay, which is sort of like to break apart or to fall apart. All isotopes of elements that are 83 and higher. So if you look on the periodic table, so Bi, which is bismuth, so it's like the next to the last in the big block. From there, greater, all of those have radioactive form because they all have so many neutrons. They're so large in size, so they are constantly in this process of trying to break down, become smaller, become more stable. But there are some smaller elements. In fact, like carbon-12 or carbon-14 is a radioisotope. So smaller elements, some of them are unstable. Most of them, the smaller they are, the more stable they tend to be. So they discovered that there's ways that these atoms break down. And we're going to talk about these three. So we're going to talk about what's called alpha decay, beta decay, and gamma decay. We're really not going to cover the positron and the neutron decay. They're less common. So alpha decay is what happens when the nucleus of a radioactive substance spits out a helium nucleus. So helium is over on the top right corner. The nucleus of the helium has 2 protons and 2 neutrons. So if you look at this, the symbol that they use He for helium. They have the 4 above because it's going to have the particle that comes out is going to have a 4 as its mass. It's going to have 2 protons. It won't have any electrons. It's really just coming out of the nucleus. 2 protons and 2 neutrons get shot out of the nucleus. And so they call it a helium nucleus. So uranium does this. So uranium-238. So you can see uranium's all the way down on the very last line, 92. It undergoes alpha decay. So when uranium loses 2 protons and 2 neutrons, what happens to its mass? It'll go down by what? Go down by 4. So the mass will decrease by 4. Remember, a proton weighs 1 and neutron weighs 1. So if we lose 4 of them, the mass is going to drop by 4. So instead of being 238, what will it be? 234. But it loses those 2 protons. So what's that going to do to its atomic number? It's also going to go down by 2. So the atomic number will decrease by 2. So instead of 92, it will be 90. So the mass decreases by 4, the atomic number decreases by 2. So is it uranium anymore? If it has an atomic number of 90, where's 90? TH, which stands for thorium. That wouldn't be something that you would have to know. It's not one of yours. But do you see that it actually changes the element? You can recognize this because of this helium nucleus. So you will see this as one of the products. So californium, which is CF, it also undergoes this alpha decay. So what would that be? Californium 257, 253, and 96. Top number goes down by 4, bottom number goes down by 2. And when you look on the periodic table, 96 is? That is curium. Stands for Marie Curie. She was another one, worked with Henri Becquerel in doing a lot of this research. Beta decay, on the other hand, in the nucleus of a radioactive atom, if a neutron breaks down, it becomes a proton and an electron. So a neutron breaks down into a proton and an electron. The electron can't stay in the nucleus, so the electron gets kicked out of the nucleus, and so what you see coming out is this electron. So the symbol, the little 0, they use a 0 in the top left corner because it has no mass, right? Electrons have no mass. You use a -1 because you make a neutron into a proton. So that means the atomic number is going to change. So in this one, with beta decay, the atomic mass, if a neutron becomes a neutron has a mass of 1, but a proton has a mass of 1. So the mass has no change, so it stays the same. So if we're looking at carbon-14, the mass would stay the same. But the atomic number, since that neutron converts to a proton, the atomic number would increase by just 1, because you're going to make a neutron into a proton. So instead of being 6, it'll be 7. So if the atomic number changes, does the element change? So the atomic number will increase by 1. And the element has a new name. So what's this one? Yeah. In fact, with nitrogen, look at the atomic mass of nitrogen on the periodic table. It's 14.00674. So 14 is the most common atomic mass, the most common isotope form. So you've gone from making a carbon atom that had 2 extra neutrons, converting it into a nitrogen atom that has the normal number of neutrons, a much more stable atom. So this breakdown is going to create something that's more stable than it was previously. How about copper? Copper 66. So if you see the 0, it means that there's no change. So 66 stays the same. The -1 indicates that the proton number increases by 1, so that's going to be 30. Atomic number changes, you've got to look at the periodic table. What's that new element? Brings it more balanced. Converting a neutron to a proton creates a more stable balance of protons and neutrons in the nucleus. So that's really what's happening in beta decay, is you're just converting neutrons to protons to try and get proton and neutron numbers a little closer together. Okay, so the last one. The last one is gamma. So gamma decay, this is the highest amount of energy. This really comes when protons and neutrons shift around in the nucleus. Nothing breaks down, nothing gets shot out, but there's energy released. This shifting causes energy to be released. So there's no particles kicked out, there's no mass change, there's no atomic number change. So if the atomic number doesn't change, the symbol doesn't change either. So what you start with and what you end with really is exactly the same. The symbol they use for this is the Greek symbol for gamma, and it kind of looks like a figure 8 without the top. With alpha, they use that little Greek A, so alpha looks like that. When they use beta, beta is the capital B, but it has like a little foot sticking off. And then with gamma, they use, looks kind of like that. That's sort of the best way I can draw it. But if you see this, you know that your starting material and ending material is still the same. So this is plutonium-250. So plutonium would still have a mass of 250. It would still have an atomic number of 94, and its symbol would still be Pu, plutonium. So really this is nothing. This just represents this energy. In fact, gamma is the most like X-rays. So most people are more familiar with X-rays and the energy aspects and blocking, shielding X-rays than they are with radioactive substances. But X-rays are not actually from radioactive substances. Instead, what they do is they have a metal, most commonly it's tungsten, and they expose this metal to a beam of electrons. So it's kind of like high electricity being bombarded on this metal, and what it causes the metal to do is it releases energy. Those energy waves are your X-rays. They are not as strong as gamma, but they're pretty close. These waves have enough energy that they can pass through soft tissues of the body, but they get blocked by bone. So they found that this was very useful as a way of being able to image hard structures inside of the body without actually having to do surgery. So you place a film on one side, you expose that body part to this energy. Wherever it's soft tissue like muscle and skin, the X-rays pass straight through. Any place that there's bone, it's blocked. And so the film doesn't get exposed in those areas. So when they develop it, they can see any small cracks or fissures, any injury to the bone, because that'll be areas that the energy waves can pass through. So a little more about this energy. Energy, whether released by X-rays, energy that's generated through alpha, beta, or gamma decay, that energy has the ability to cause electrons and other molecules to be affected. So this energy, as it passes along, if it touches or comes to another molecule, it can transfer energy to that molecule. It can cause that molecule to then change in its appearance, to change in its activity. It can make it more reactive. It can make it more stable. It can cause it to break down, depending on the amount of energy exposed and the length of time that ionizing radiation is exposed. A good example, a sunburn. So a sunburn is ultraviolet light. It's ultraviolet energy. So it is energy when it exposes to the skin for short periods of time. It stimulates the cells in your skin to make pigment. But if it's exposed for too long, those cells are reacted upon by that energy, and it causes damage. Then you end up with the redness, and eventually you end up with those cell layers even peeling off. So the same thing happens with radioactive substances. This radiation energy has the ability to cause damage to other molecules, eventually causing damage to living cells. It can change structures inside of the cell like DNA, and can even cause damage to the controls over cell growth. And it can lead to abnormal cell growth, which is what you associate with cancer. So if you're working with X-rays, if you're working with any radioactive substances, then you want to know how strong this energy is and how to block or shield yourself from exposure. So just as general precautions, you wear a lab coat, you wear goggles, you wear gloves, you don't come in direct contact. You may need to use shielding with radioactive energy. And most people now, they wear what's called a film badge. And so this is a badge that they can check every month and see how much exposure did that film on the badge have, because that is an example of how much energy you have been exposed to above and beyond normal because of your job, because of your X-ray work. With a lot of X-ray techs, it's not as much of an issue. It's really more of an issue with people that have to actually be standing next to the patient when they're having X-rays, multiple X-rays done. So in looking at shielding and looking at penetration, you could say in general, the bigger the particle that's getting shot out of the nucleus, the slower it moves and the shorter the distance. So alpha, remember we said alpha is like a helium nucleus. So alpha particles have like a mass of 4. They don't go very far. They actually only move a few inches. So if you had an alpha sample, if you were more than this far away, those particles, that energy is really not going to cause any damage. You can block this with paper, with saran wrap, like having it in like a Ziploc bag, like a thin layer of plastic wrap, that type of thing. If it does come in contact with the body, it only goes in a few cell layers. So it's a very short distance away. So with alpha, you're only talking about just 10 to 15 cell layers. So it really can't even penetrate all the way through the skin. Beta, on the other hand, remember, that's an electron getting shot out of the nucleus. It's smaller and it moves faster. So it actually moves a few feet. So if you have a sample, if you're standing a couple of feet away, that energy is not going to reach you. But it has the ability to penetrate into tissues. So it doesn't penetrate all the way through, but it would penetrate into the tissues underneath the skin if you were exposed superficially. So in order to block this, you use aluminum foil or you use plexiglass. Yep, can penetrate into layers under the skin versus right on the surface of the skin. So you can block with some heavy-duty aluminum foil. Or plexiglass. So plexiglass is like what they use at the hockey rink, like that's the glass. So it's usually about a ½ an inch thick. That's thick enough to be able to block that energy from passing. So you would typically keep a shield like that between you and the sample you're working with. But gamma rays and X-rays, remember, there's no particle. These have the highest amount of energy. These can travel 100 meters or more. Much further distance they actually pass straight through you. Gamma rays pass straight through you. So that means all layers of tissues can be affected by that energy. So you're not just going to have the skin affected. You're not just going to have the surface layers underneath affected. You can end up with effects that are in the bone. You can end up with effects on organs. You can end up with effects that are much deeper than any of the others. So to be able to block this, you use a lead shield or concrete. That can block the energy from being able to pass through because it's a really dense, heavy structure. So those energy waves don't pass through. So this is just one that's sort of like I said, just a couple of inches, a couple of feet, but then you're talking about several meters to several hundred meters. Tissue penetration, and then how to protect yourself. So this sort of summarizes those. So when you have X-rays done, they use a lead apron. Where do they put it? What are they trying to cover? But most specifically, what part of your body do they try to keep covered? Not your uterus, but the ovaries and testes, the gonads. And that is because that is where egg and sperm are located. And so if energy affects them, that could lead to damage to developing egg or sperm, and that could end up leading to birth defects in offspring. So it's most of the time they always make sure that they cover the area from your waist down through your hips, and that's really why.
Is that why they always ask you before they do the X-ray if you're pregnant?
Yes, because if it's an avoidable X-ray, they're not going to take it. Even with the apron, even with the shield, they're still going to avoid it if possible. And that's really the reason, is it's to protect the ovaries and testes. Because that is a location of the sex cells, and damage to them could lead to injuries, birth defects to any offspring. So when you have a sample of this radioactive material, it really depends on what that material is as to how long it hangs around, what kind of energy it's releasing. So they came up with units. So when you talk about the activity of a sample, they use the becquerel and they also use the curie. This is the much more common energy unit for a substance. And when they talk about its activity, it's how much energy it's releasing. So it could be releasing 100 curies of energy. That energy can actually be detected or picked up using what's called a Geiger counter. And they define radioactive substances based on, well, how long does it take for half of it to disappear? So if you start off with 100 curies, how long does it take for it to only be 50? And then only be 25? And then only be 12 and a half? How long does it take for this substance to break down? Because it's always breaking down to become more stable. So they call that half-life. So half-life, just by definition, is the amount of time it takes for half of your sample to disappear. Most medical amounts, like if they're using this either diagnostically or therapeutically, if someone's undergoing radiation treatment, or if they're trying to determine activity of some organ in the body, they use very small amounts. Instead of curies, they'll use millicuries, which is a thousandth of a Curie. So they're going to try and use the smallest amount possible, just because it's always releasing this energy that could potentially cause damage. So in looking at them, we have some, these are natural. These are the ones used in medicine. So these are actually man-made. Naturally occurring radioisotopes, like hydrogen-3, called tritium, carbon-14, radium-226. These ones have years. Their half-life is really long. They don't break down really quick. That is one of the challenges, like for a nuclear power plant that uses things like plutonium and uranium to generate energy. These things are around for 4.5 billion years. So they're releasing a lot of energy, but for a very long period of time. And so there's always the question of, well, what do we do with this stuff? Like when we're done with it, like where are we going to put it? Can't we just scatter it all about back into the earth? That would really be the optimal thing, because that's what they did, is they collected it out of the earth. And so it needs to be dispersed back in. But it's a big challenge trying to figure out how to get rid of it. But stuff that we use for medicine, you have minutes, hours, maybe days, but much shorter, because you don't want it to be affecting your patient for a long time, for years after you're actually administering it. So when determining half-life, you look at how long the half-life is, and that means that period of time, half of your sample will be gone. So in this, if you have a patient and you inject them with 150 millicuries of iodine-131. So iodine is an element that actually gets concentrated where? Where in the body? There's only one place. Where? The thyroid. The only place in your body is this small bilobed gland that's in your neck, called your thyroid. It creates a hormone called thyroid hormone. Thyroid hormone contains iodine. That is the only place in your body that iodine is needed. So you get small amounts in your diet. If a patient has an overactive or underactive thyroid, then they need to be able to monitor and see how active it is. So they may give them an injection of iodine-131. Iodine-131 breaks down every 8 days. So if you start off with a sample, in 8 days, half of it will be gone. In another 8 days, half of that will be gone. And so each time you just divide it by 2, divide it by 2. It's always going to decrease in half. So this one says, how much iodine would remain in 32 days? So the first thing in this you have to figure out is, how many half-lives is this? 32 days is how many half-lives? (32) divided by 8 tells you there's 4. Okay, so that's 4 half-lives that go on. So if we start off with 150, in 1 half-life, how much would be left? Divided by 2. So in 8 days, you would have 75. And then in 8 more days, this will be 2 half-lives. Half that number, 75 divided by 2, would be I got 37.5 millicuries. But you're not done. So you got one more. Nope, 2 more, sorry. The next one, so take 37.5, half it again. So every 8 days, half of it will be gone. 75 millicuries. So that would be the third one, but you'd still have one more. So the fourth Could be 9.375. So that would be in 32 days. So the first thing with this is just figure out, okay, well, how many half-lives have gone on? And then just go half it each time. Divide it by 2 each time to figure out how much would be left. So you can see in one that has a pretty short half-life. So in a month's time, you've gone from 150 to 9. So you've reduced it by like 95%. So most of it is gone. Most of it has decayed in that period of time. So this is used for therapy. But there's iodine 123. There's a second radioactive isotope of iodine, and it only has a half-life of 13.2 hours. So that is much faster. It's going to break down, and it can be used in very low levels diagnostically. So they give you an injection of iodine 123. It gets taken up, and it gets collected in the thyroid. Let me show you the picture. So a normal looking thyroid, because your thyroid is this bilobed gland. It's got like kind of 2 lumps, and there's a little bridge that connects them right underneath where your larynx is, like where your Adam's apple is. So that's where it's located. And so when they inject with this iodine as a diagnostic tool, they give you really little amounts. They use that iodine 123 because it doesn't have it has a short half-life. That iodine gets taken up, and they can use a monitor. So they have like a monitor, a sensor that actually measures where that iodine goes. So in a normal looking thyroid, do you see how it's kind of uniform? So it's sort of all even, and that's what the detector will show. But see the bottom one. So see how the bottom one, how it's sort of out here? They're not very symmetrical. They should look the same. And over here, it's light in comparison to the normal. That shows an area of low activity. So it could be that those cells in the thyroid aren't using the iodine like they should. Sometimes it'll actually turn out and have a really dark area, which shows that it's taking up more iodine than it should. You should have sort of uniformity throughout. So it can be used as a way to diagnose thyroid issues without having to do surgery. Using iodine 123, short half-life, it's gone, 13 hours, half of it's gone, another 13 hours, you're down to 75% gone. Every time you're halving the amount. Short half-life allows you to see activity of the thyroid without surgery. They try to use, when they're doing diagnostic, you want to use radioactive substances that break down quickly, that go in very specific places. You don't really want one that's just going to be scattered throughout the body. You would want to use something, iodine's optimal, because it's going to go really only to the thyroid. It's not going to collect in the liver. It's not going to collect in other organs. And they want one that has this short half-life so that you can get rid of it quickly. So if they show that there's an over or underactive thyroid, that there's an abnormal behavior of the thyroid, oftentimes they will try medication to just get the thyroid kind of on an even keel. But if they can't, they can go back and use what's known as a therapeutic dose of iodine 131. It has a longer half-life, which means that it's going to collect in the thyroid, be releasing its energy, cause damage to nearby cells, and in a month's time, that's like the half-life is 32 days, so in a month's time, you will actually begin to see activity of the thyroid decreases. So you're effectively killing the thyroid this way. You kill the thyroid cells by exposing them to that radiation because those cells are abnormal. The cells are overbehaving, they're overactive, and you can't control it with other medication. So again, this is a way you can do this without having to do surgery. What do you have to do though afterwards? Once you treat a patient with iodine 131, now they don't have a thyroid. Their thyroid's not functioning, so then they actually have to take medication for the rest of their life. While a patient is undergoing thyroid treatment with iodine 131, there are some health aspects that they have to treat. The patient should sleep in a separate bed, wash bedding separately, use a separate toilet from everybody in the house if possible. So why? It's because they may be sweating small amounts of iodine. So most of it would get concentrated in the thyroid, but they still may excrete small amounts of radioactive iodine during treatment. So sleeping in a separate bed, then that way you're washing that separately, using the toilet separate from everybody else. They tell you to like double flush just to make sure that you do rinse everything out of the bowl so that nobody else in the household is being exposed to that energy. So those safety precautions are really for everybody else that's in the house, to try and reduce the exposure of everybody else to any of this radioactive energy. Here's the other one. So like I said, in diagnosis, you want to really trying to use the least amount and try to have very short half-lives when you're trying to diagnose. If having to use therapeutic doses, that is going to be using higher doses. They try to use a radioactive substance that will get concentrated in one area, not spread throughout the body. There are some radiation treatments. There's that, this one's like colorized because everything's done by computer. That one on the left is normal looking thyroid activity, pretty even in both of the lobes. But then can you see over on the other one how that right side doesn't have the same coloration pattern? That always shows up as something unusual, something abnormal. So that's really what they're looking at when they do the thyroid panels, the diagnostic. They can use radioisotopes for cancer treatment as well. Most of the time they use what's called an external beam. So this is when you do have a radioactive substance, so it's not just an X-ray. So it is a radioactive substance. Oftentimes they use cobalt-60 as a common form. So they expose the area to this cobalt-60, and the goal is that the cobalt-60 is going to penetrate far enough into the body to cause damage to tissues, causing damage to cells that are growing faster than they should. And that is a characteristic of tumor cells, of cancer cells, is that they grow without any kind of cell cycle control. So if you can cause damage to them, that'll stop them from growing, and so that's going to stop the tumor or the mass from getting any larger. But what other things do you have? What other issues? So if you're exposed to this from this external beam, that means your skin is exposed, the underlying tissues are exposed. It's not just the cancer that is exposed, so you end up with side effects. So what happens to that area of the skin? It can break down. It can oftentimes look like it's a burn. It'll look like a bad rash will develop in that area. So it's not just the surface, the epidermis, but you can even have areas of the dermis that get irritated and you get sort of a rashy type of sore. If you're doing spot radiation, that's optimal because you're only going to expose certain body parts. But if they find that you have abnormal cells that have spread, then they may have to do whole body radiation. So whole body radiation means that all of the body is exposed, and there you can end up affecting hair growth, so hair loss, because your hair follicles are areas of rapidly growing cells. Your GI tract, like your tongue, your taste buds are replaced every 3 days. And so those, oftentimes people say that their taste goes away. Food doesn't taste as good, that they don't really have any kind of taste. It can also affect the lining of your GI tract. So a lot of people experience symptoms of diarrhea, malabsorption of nutrients. So they actually start having malnutrition. They might eat, but it's not getting broken down and absorbed as well because of that lining. And a lot of times it causes nausea. So patients get really sick and nauseous, can't eat, can't keep things down. All of those can come into play. Those are all side effects of this exposure to this energy. So that's external. There are even internal. So there are internal radioactive implants that can be used. One of them is what are called seeds. So that you can see in this one, they use titanium because titanium doesn't rust and it's not typically not reacted upon by the body. So that's why they use them for like implants and like hip and bone replacements. So the titanium, they take these small, they look like pencil leads because that's a penny. So these things are really tiny. They actually coat them with a radioactive substance, usually an alpha emitter, usually something that doesn't go very far. So if you can place that seed in a tumor, it is only going to affect the area right around it, which would just be tumor cells. So they use this for things like prostate cancer. It's a really slow growing cancer, but that's a way to be able to treat it. Sometimes they remove the seeds, sometimes they just leave them in. Just depends on the amount and the decision with that. They're going to use something that's more alpha decay. Lung cancer, treatment of lung cancer, they actually use a radioactive xenon gas. So the patient inhales this gas, it coats the linings, which is where the most common place that you find abnormal cell growth in the lungs. It's all along those airways that you see it. And so this is a way of actually sending the gas to that area without having to do surgery. Because it's always the biggest challenge of trying to do surgery, trying to minimize scar tissue and still have remain function, but trying to make sure that you get everything. And with lung cancer, it's a really big issue because of those soft, spongy type of tissue that it is and the amount of oxygen it's exposed to. So there's multiple ways that you can use radioactive substances. The key thing, if you're taking care of patients that have any type of brachytherapy, seed implantation, have gone through any type of treatment, really making sure that you reduce your physical exposure to their skin just because of secretions that may possibly sweat, any other excretions that may come from them. All of those could potentially, if they've had any type of implant, could potentially then have the radioactive substance, small amounts of it. You really try to limit your exposure. And if you're handling patients that have any of these, you really want to make sure that you have a film badge. You want to have a way of being able to monitor how much am I exposed to in my job as I'm going through on a monthly basis to make sure that you're not overexposing yourself. There is, let's do another one, this one. So this is actually from chapter 2, question 77. So iron 59 has a physical half-life of 45 days. So if you get 168 grams of this sample in the lab, what % of the original sample remains after 270 days? So the first thing that you need to figure out is what? How many half-lives have gone by? So if its half-life is 45 days and you've had it for 270, then you just have to do that division. So one half-life is 45 days. So just dividing comes out as 6. It's just gone through 6 half-lives. So if we start off with 168, In one half-life, how much will be left? 84 grams. So in a second half-life, 42. Third half-life. Fourth. Mm-hmm. 5.25. And one more. Not much. Starting with 168 grams, you'd have like 2.5 grams left. So it would just slowly decrease over time. So the actual amount decreases in grams. It's also activity. If you were measuring its curies or its millicurie concentration or activity, that would all decrease in half. So that's what you do with each one. If you're given, they'll always tell you like what the half-life is. And so you have to figure out how many half-lives go on, and then just do a half-life. Each one, it's half of it along the way. I think there was one others. Yeah, so a patient is injected with iodine 123. The half-life is 13.2 hours. How long will it take for 5 half-lives to pass? What do you think? So if 1 half-life is 13.2, and you want to know how many 5 are, it's just a matter of multiplying the two. 13.2 hours times 5. So it would take 66 hours for that time to go by. So there's one other diagnostic tool that they use. It's called positron emission tomography, or PET, a PET scan. So this actually uses the type of decay we didn't talk about, but you can get the idea based on alpha, beta, and gamma decay and what happens with this type of decay. So they usually use fluorine 18. So fluorine is one that is taken up. It breaks down into oxygen. So as it goes through this, it releases gamma radiation. So that is this radiation that accompanies this breakdown. That radiation can get picked up by a scanner. So what they do is they link this fluorine to glucose. So they link it, so it's a glucose molecule and has a little radioactive fluorine hanging off of it. They inject it into the patient. Glucose, one place that glucose can get taken up by cells, whether insulin is present or not, is the brain. And so this has been found to be very useful in monitoring brain activity. The brain is notoriously difficult to monitor activity because you've got the hard skull that protects it. So doing an X-ray is all you see is just the skull. Being able to actually measure what's going on inside in this three-dimensional space, this has really helped greatly in identifying and diagnosing some of the traumatic brain injuries that previously they really didn't even understand. Because if you didn't get a concussion that caused brain swelling, if you didn't end up with a brain bleed, and you didn't have cognitive changes immediately obvious, a lot of those injuries would have gone unnoticed. So what they do is they give you an injection of this radioactive glucose. It's just a sugar solution, but it's taken up and it goes into the cells of the brain because it doesn't matter if insulin's present or not. And so then they can talk to the person. They can have them actually think about things, imagine things, look at objects, and you can see different parts of the brain light up as they're being used. So you can see parts of memory, those areas of the brain light up. If they ask you to read something out loud, the parts that are associated with language will light up. When asking them to look at things, the parts associated with visual and association, they light up. So that actually allows them to ascertain all of these are normal. Here's an example. On the left is processing of memory by a normal person. So the red areas show activity, the yellow is lowered activity, the blue is less activity, and the black is no activity. So you don't always need to use all parts of the brain for all processing. So you can see activity scattered throughout. But the one that's on the right, that's your Alzheimer's patient, doing the same activity. So they're asking them the same questions, drawing on the same things, and you can see how much less activity those cells have in comparison. Because in Alzheimer's, the cells begin to develop scar tissue, these neurotwists that end up decreasing activity, loss of connections between brain cells, between neurons, and that is why they begin to lose their memory, they begin to lose coordination, they begin to sort of like revert back into more childlike behaviors. That's all because of this disintegration that occurs of the neural structure. So it's a good one that shows just how much this radiation and understanding of nuclear chemistry really has helped with diagnosis. There's still no big cure for Alzheimer's. There's still a lot of research that they need to do to try and slow down that damage that begins to occur. But it is at least a way of being able to say, yes, this is happening, instead of just saying, we don't really know what's going on. So the diagnostic tools that like avoid surgery really are a help. Okay, so I will quit there.